Hello, my name is Joshua Clark, and I'm going to be going over my term project for my ECE4380 Power Systems with Renewable Energy at California State University, Bakersfield. Here is just an outline of what I'll be going over in this presentation. First, I'll be going over what a hydroelectric power plant is, the real basics of it. I'll then go over the academic journal, which was what the term project was about. My academic journal is called the Steepest Descent Algorithm for the Optimal Control of a Cascaded Hydropower System. I'll then review the specific issue of achieving power optimization of these two power plants, which are located in Nigeria. I'll then go over the solution for optimal control using the Steepest Descent Algorithm, then go over the results and analysis found by this team, and then finally a conclusion. So here we're going to go over the basics of the three different types of hydroelectric power plants. One of the first systems that's most well commonly known is a dam, and that one basically just holds water up in a reservoir and releases it as when power is needed. That water flow is converted from potential to kinetic energy, and that kinetic energy is captured through a turbine, which is spun, and that spinning motion is connected to a shaft, which is then used to produce electricity. A diversion facility is similar to that of a dam, but less intrusive to natural habitats. It works in that it uses the natural flow of the river, but only uses a small portion of that river flow, diverting it using either a pipe or a man-made channel into a power facility, which once again converts the water flow into electricity and then dumps that water back into the river downstream. Finally, a pumped storage facility is kind of like a battery in that it's charged and discharged depending on when power consumption is needed. We'll go into more details on how each of these work. First, a dam, probably the most commonly known system. Here on the left side of this diagram, you can see water's being held at a higher altitude. The water is then released by control through this inlet down to a turbine, which is spun, and above that turbine is a generator where the electricity is being generated. The water is being then released out through the tail race at the bottom right of the diagram. Here is the diversion facility. This one uses a portion of the water flow here at the top right of the screen or the diagram, and then carries that water to the left and transfers that to a power facility at the bottom left of the screen. That water is then released back into the river downflow. And once again, this one is less intrusive than a dam in that it only uses a portion of the water and doesn't need to say change the whole habitat of the area. Finally is a storage pump facility. This one is unique in that water isn't being used to generate power all the time. Instead, this reservoir is being used to store and release the water when power is needed. So at night, this reservoir is filled, and during the day, the water is then released. And you can see here, if you look closely, there's a little white rectangle. That's where the power facility is. And as the water is released back into the river, that then generates power when power consumption is needed. So now we'll start to go over the academic journal. This is, once again, it's called the Steepest Descent Algorithm for Optimal Control of a Cascaded Hydropower System. So just as mentioned before, in the country of Nigeria, there are two cascading hydroelectric dams. And the issue is that this team of computer engineers and electrical engineers want to optimize the power generated by these two hydroelectric dams. Some of the factors that causes issues are the weather-related factors. Heavy rains or no rains can cause power reliability to be hampered. So we want to make sure that we can be able to control as much as we can, even though weather is we have very little control of the weather, and also the availability of these power generators. Even though we'll have the water to potentially create the electricity, that won't necessarily mean we'll be able to do it because some of the generators may be in maintenance or repair. So the solution this journal proposes is to optimize the energy being produced at each dam. And to do so, they go heavy into mathematical calculations. One of the ways they optimize this method is by setting limits rather than the infinite dimensional um, system. They create a finite limit to the steepest descent algorithm, as well as using Excel VBA, Visual Basics application, which is basically just like Microsoft Excel. It's going to help you solve some of these Lagrange problems, which are going to require multiple iterations. So here is an attached image of a map of Western Nigeria. It shows the two locations of these two hydroelectric power facilities. The one up north is the Kainji Hydroelectric Power Station. This one is upriver from the Jebba facility, the Jebba Hydroelectric Power Station. Both of these reside on the Niger River, and it's prevalent to see that the water that's released from the Keeps facility is then sent downstream to the JEPS facility. So these two in tandem need to work together to be able to optimize the power to produced for these two hydroelectric power stations. So it's crucial that these two be in tandem and work together. Here we can see a closer image of these two facilities. The Keeps, built in 1968, capable of producing 760 megawatts of power. The Keeps uses a Francis turbine design, and we're going to see how that's actually kind of a design flaw. It changes the direction of the water flow to produce electricity, and it's just not the best design. The Jeeps facility was built in 1985. It's capable of producing 578.4 megawatts. This one uses the Kaplan turbine. This one is better in that it doesn't change the direction flow of the water. However, the blades of the propeller are fixed, which aren't the best. So both of the facilities have their design flaws, but you get what you get. So still, we're going to try to maximize the power generated using these two systems. And closely is just a look at these two turbines mentioned before. The Francis on the left, the water goes through the left side of the image, spirals through this turbine that's spun, and the water is then sent down out the tail race. Now you can see the water goes from a horizontal to a vertical motion. So that right there is the design flaw, or not best, because some of the energy is lost by doing so. It's not clear, but these turbines are kind of like a shovel shaped, and that water can be fed down as they're being spun. And on the right is the Kaplan turbine, much simpler design. Water is being fed from top to bottom, never changes direction, spinning this propeller. Now, as you can see on top, this would be the most sought after design, where the turbine blades can be rotated, changing the speed of the shaft to generate electricity. Alright, so now that we know the issue at hand, we can start applying some mathematics to attempt to maximize or optimize the control system of these two hydroelectric power stations. First, we'll want to start to declare some variables. Most importantly, though, we'll want to create this performance index function called capital J of H of U. It's going to be a nonlinear differential equation, and we're we are concerned about the gradient of this performance index. If you recall from your calculus class, the gradient points in the direction of a greatest increase. Well, we actually want to go in the opposite direction. So we're going to find the gradient, but go in the opposite direction of that. And that's going to help us optimize the control system for power generation. Along with the power index function, we also have a collection of variables here on the right of the screen. T for time, H for the operating head size, that's going to be in meters. U is the control signal, that's going to be a function. N is going to be the number of operating units. A is the surface area of the reservoir. A2 is going to be the surface area of the scroll casting, that's the turbine. G is the physics gravitational constant. Q sub J is the inflow into Jeeps. Q sub L is the evaporation loss at the Jeeps reservoir. Q sub S is the spillway discharge from Jeeps. Small q sub k is the discharge from Keeps trail race, so that's from Keeps going to Jeeps. Big Q sub sk is the spillway discharge from Keeps. Big Q sub cj is the inflow from the catchment area between Keeps and Jeeps, so the reservoir size, and f is the nonlinear function. Here we have the control signal function u of t, which is going to be used to determine the optimal control that's released from Keeps to the operating head of Jeeps, h of t. That's going to be created in this nonlinear differential equation on the right-hand side. We're going to go ahead and set a limit to the time, and that's going to be from the initial time t naught to the final time t of f. That is going to be the finite limit that is going to make this more optimal than previous mathematical calculations. The nonlinear differential equation is used because of the changing dynamics at the operating head h of t. And using all of these three, we can actually create a standard form. H of t is equal to the function of h of t, u of t, t, where t is bounded between t initial and t final. The performance index accommodates a penalty deviation specified at the head to ensure that the control does not require more than what is capable at the Keeps facility. So if we have an infinite value with no limit, even though theoretically we could produce this much, realistically we couldn't, because there's actually a limitation of the power being able to produce at the Keeps facility. So we set this limit where I is equal to the min j, the performance index, which is then described in this integral. H of capital T is the desired value of kh. Capital KH is a positive weighing constant. And some of the constraints are here at the bottom left. Some of them just kind of reinstating what I just said. Here we have the steepest descent algorithm, which we want to minimize as much to 0 as we can. We're going to go ahead and use that to create a unit vector in the direction of the gradient. And because we want the opposite direction, we are going to go ahead and put a minus sign in front of that. Now, psi k is the optimum steepest descent step interval. This is going to be another way that we're going to be able to optimize the performance index and the control system, is by finding the smallest step size to optimize the calculations, speeding up the calculation process. A very clever method to solve for that psi k is using the quadratic approach. So here we notice that we can go ahead and use the quadratic equation where psi sub k is going to be equal to negative b over 2c, and then we also have this nasty equation here at the very bottom, um, which we're going to go ahead and use in Excel VBA later. So now that we have the necessary equations to solve for the steepest descent algorithm, we can go ahead and start using the Excel VBA to help us solve for those. We're going to go ahead and start with k is equal to 0 and go from there at different iterations. The nonlinear differential equation is going to be solved using the Adams-Moulton technique along with the Adams-Bashforth technique. Those are two methods for solving nonlinear differential equations. Those are pre-programmed into Excel VBA, so we won't have to worry about those. From there, that will give us the performance index. We'll then have 4 different iterations of the performance index. For each of those, we'll want to solve for the gradient, and not just that, but also the unit vector and the direction of the gradient. And then we'll be able to obtain the big picture, big U of k, where then we'll be able to solve for psi min by having it in this matrices format, and then using the quadratic method where we found psi min, which is negative b over 2c, I'm sorry, and then be able to compute the control vector. That's all using Excel VBA. And that will be repeated multiple times until convergence is met. All right, now that we performed those calculations, we can go ahead and depict them on graphs using still Excel VBA. So there are 3 different cases that we're going to consider. The first one shows where if we had no limit, this would be just like if we had done the calculations beforehand, before this proposal was made. This is how the calculation would have been performed using the direct method. And here it shows that convergence was met after 15 different iterations for the trajectories of h of t. And over here, well, on the left side, it shows the black line, which is where the convergence was actually met. And then on the right side, the bar graph shows the performance production at the Jebs location based on the no limit values we gave it. Here on the x-axis, the U subs are the how much output is produced at each interval. These are spaced out between 6 hours. So you can see here it starts very large at 7,127 meters cubed per second, and then drops dramatically to 470 meters cubed per second, and then kind of tapers off at around 1,700 meters cubed per second. So very dramatic influxes within just a short time period of 6 hours. You can go from very high to low, which is not reliable. So now with limitations, we have this this new computation. So we set the limit to the Keeps maximum, which is 3,000 meters cubed per second. The computation took 54 iterations, however, it converged faster. So even though it took more iterations, the calculation was performed faster, and a much more cleaner and appropriate look, as you can see on the right side, the bar graph. You can see that the maximum is reached at the first 3 intervals, and then tapers down to 1,100 meters cubed per second. So it shows a much more controllable, reliable source for power. And here we still have that same limitation at 3,000 meter cubed per second, But here we're limiting ourselves in that only 3 machines are being used, 3 turbo alternators are being used to convert that water flow into electricity. So this is the scenario in where not all of our power generators are being used. So if only given 3 machines and still setting the maxima at 3,000 meters per sec, 3,000 meter cube per second, we see that it only took one iteration to converge, and that the outflow is tapers slowly, very slowly downward, starting at 3,000 and ending at 1,300. Even though this isn't optimal, it does actually, it is still more appropriate in that it's not as dramatic, the decrease. And so, in conclusion, it shows that even though with such a unique problem such as this, 2 cascading hydroelectric power plants, electrical engineers and computer engineers are always striving to optimize these 2 systems. So it just goes to show that, well, even though we do things one way, things could always be better. They did so by keeping the Jeep's head size relatively constant when performing the Lagrange problem for optimal control. They also use the Excel VBA system or program to perform the calculations in iterations. They set a limit to the infinite integral, which allowed the convergence to happen quicker. And they use the quadratic system to find the steepest descent size. So I hope that you were able to learn something from this presentation, and thank you so much for listening.